Welcome back to Differential Equations. In this video, we're going to be looking at some numerical tools for ODEs. Specifically, we've looked previously at Euler's method, and we've seen that while you can solve a first-order differential equation using that tool, it's not the best. And luckily, there have been improvements made on it. This is not a course in numerical methods, so I'm not going to get into the details of how and why it works, but I think that it's important for any student of differential equations to have at least heard of the Runge-Kutta algorithm, named after two computer scientists. There are a couple of these algorithms. The most popular variant is the fourth order algorithm, which is sometimes called RK4 and sometimes called RK45. The reasoning behind that is entirely based on how you are calculating error. Runge and Kutta were looking at the truncation error that we talked about in the video on Euler's method. There are other things that computer scientists like to talk about concerning error that would call it a fifth order error instead of a fourth order error. Again, well beyond the scope of this course. I'm not worried about how it works. I'm just worried that it works. So I don't want to try to learn how to implement this. I want to learn how to use it where it's already implemented. All right, so here I am in a Python notebook. This particular notebook is hosted on Google Colab, and I have it available that anyone can look at it but not modify it. If you would like to modify it, the first thing to do, well, first of all, is log in with your Google account. Your school-issued email address is a Google account, so you can use that. Open this up, and then go into File, and save a copy in Drive. That will give you a way of working with this so that you can save your work, you can edit the file, you can reuse it as you see fit. I have a bit of an explanation here reminding you that this is the Runge-Kutta algorithm. The first bit of the code is just asking us to tell Python that we want to use the integration package. So SciPy.integrate, which I abbreviate as SI because SciPy.integrate is just entirely too much to type out. But that has the Runge-Kutta algorithm already implemented. Somebody has already done all the work, and we're just going to use it to our advantage. I also have the PyPlot library, which I abbreviate as PLT, which will allow us to graph our solution when we're done. And I have the NumPy library, which I abbreviate as NP, and that gives us access to mathematical functions. It's a little bit annoying. We have to put NP period in front of every function that we need, but if we want to take a square root, a sine, exponential, so on and so on, that is the tool that we want to use. So we're trying to solve a first-order linear initial value problem. We are going to have it in this form. That is the form that we've been dealing with. Nothing new there. Although it is full of subscripts, and subscripts are hard to deal with, so it's a little bit weird to see all of this written out, but it has what we need. We need to define that function, f of t and y, that is the right-hand side. You can see in this case that my right-hand side is just cosine of t. So once again, this is a differential equation that we could solve easily. This one could be solved using direct integration. We have y prime equals cosine of t. Integrate both sides with respect to t, you have your solution, nothing else to do. We have our initial conditions. T naught, t subscript 0, y naught, y subscript 0. We need to tell Python what value of t we care about. And I've told it here that I want to go up to t equals 8. And then we need to tell it our time step. I've given it here delta t equals 0.1. You are welcome to change any of these to match what you need for your problem. One of the things that I want to point out, coming back up here, the most common mistake that I see is errors in typing out your function. So I had cosine of t as what's put in here. Let's say instead we had t times cosine of t. Well, in strict algebra, it would just be t cosine t, but if you try to type this in, you're going to get a horrible error. So you have to take one more step and explicitly put in all of your multiplication. Almost all of the algebraic functions are there. You have to put np period in front of them to say that I want to use a function. If you Google numpy, it will give you all these details. Why did I suddenly go so blurry? Let me reset my camera, see if I can fix that. Hey, there we go. All right, but we have there our function. And then there is a third section of code here, which actually calls the solver. Again, everything is already set up. You don't have to change a thing here. It will do all of the work for you. And you can see that it's going to spit out y evaluated at that point t max that we care about at the end. This is the solution for the original y prime equals cosine of t. I've now changed it, and I'll run this in a minute, but there's one other thing that I had this bit of program do. I also have it creating a graph. I said do not modify this section. I think I'm going to actually delete that because you might find that it's useful to change your X label, your Y label, and your title. You can change the stuff that goes inside the parentheses here, and it will all work out. You'll notice that I have my variables t and y of t enclosed in $signs. That is telling Python that I'm using LaTeX notation in order to write mathematics. If you've seen LaTeX notation and you're comfortable using it, you can go for it. If you're just trying to write a variable, $, variable, close $, and that is easy enough. You really won't need anything more powerful than that, but I did want to point out that is a thing that's happening. All right, the parentheses and the opening quotation mark, and then the closing quotation mark and the parentheses at the end are important. You can change the stuff inside the parentheses otherwise. And it will give us a graph of our solution. All right, but again, this is the solution for y prime equals cosine of t. And I've now changed it. I have t times cosine of t, so I have to run it again. If I come up here to the top, to the runtime menu, if I've been working with this already and I've made changes, you'll want this restart and run all, that is right there. It's grayed out now because I haven't run anything yet. It hasn't started in the first place. So instead, I want to run all, which is actually the very top item on the menu. So let's run all. You can see that it has this circulating play button on all of these lines. That's telling you that it's trying to run that bit of code. Once it has run that bit of code, it replaces it with a number so that you can keep track of the order of your code blocks. But we have here our solution. Y of 8 is about 1.27. And down here we have a graph, which if you kind of squint, it looks a little bit like a sine wave, but the amplitude is increasing, which is kind of what you expect. For t times cosine, when you integrate that, you'll end up with something with a t squared. So there we have it. That is the Runge-Kutta algorithm for solving first order differential equations, initial value problems numerically. It's a little bit more powerful than the Euler method. If you're interested, it's not that far beyond the scope of this course. If you have any background in computer science, you should be able to understand the implementation without any issue at all. But for the sake of time, just knowing that it exists is good enough. Although, whoops, that's what I wanted. I didn't want to make myself disappear. While the Runge-Kutta algorithm is an improvement, I guess the natural question comes up, how much of an improvement is it? So now let me get my head out of the way. And we're not going to get into this in a lot of detail, but the error for the fourth order Runge-Kutta algorithm is generally on the order of some constant C1 times delta t raised to the fourth power, plus some other constant C2 divided by delta t. Right. It's very unsatisfying as a mathematician to teach just jumping in like this, because first of all, where did this formula come from? Well, some computer scientists figured it out, and I'm just trusting them. And second of all, what are C1 and C2? Well, they're constants that depend on the particular problem that you're trying to solve. How do we find them? I don't know. It's a little bit beyond the scope of the course to figure it out. I just want to look at this in generality, because the interesting thing is that if we pick a delta t that is very small, let's say 0.1, that's what we had been using, then delta t raised to the fourth power is vanishingly small, 0.0001. But then we have delta t in the denominator. So we also have a 1 over delta t term. And 1 over 0.1 is 10. That does not look promising. So there could be issues. There could be serious issues for certain differential equations. You have to be careful and make sure that the differential equation that you're using is actually going to work. How to figure that out is a little bit beyond the scope of this course, but I can't in good conscience wrap this video up without warning you that that's something to worry about. Luckily, we can say that, generally speaking, C1 is on the order of about 10, and C2 is generally on the order of about 1 over 100. And so picking delta t as 0.1, okay, 1 over 100 divided by 0.1 is still 1 over 10. That's still perfectly fine. And if we're lucky and say C2 is on the order of 1 over 10,000, well, 1 over 10,000 divided by 1/10 is still 1 in 1,000. It's still incredibly small. But it's always there. So I mentioned when we were dealing with the Euler's method video that this is something that you often have to worry about. If you pick too large of a value of delta t, then delta t to the fourth becomes a ridiculously large number and you have a lot of problems. If you pick too small of a value of delta t, then 1 over delta t becomes a ridiculously large number and you have problems. So there's a balancing act. It's not perfect, but the places where it is effective, it can be effective. And just knowing that there are such places is going to be good enough for us for now. All right, let's wrap up as we always do with a problem for you to solve. So we have here dy dt is equal to y squared t plus t squared. This is not separable, and it is not linear, so the common tools we have for solving first order differential equations aren't going to help us. We are stuck with, I hope there is a numerical approximation, and luckily there is. So we have that differential equation, we have that initial condition, y of 0 equals 1, and let's say that we want to go from our initial condition where t equals 0 up to t equals 5 to see what happens. All right, take a couple of minutes playing around with Python. Use my script as your starting point. Just copy it and edit it as needed to get these values in there. See what you can do with that. And I was about to say I'll see you in the next video, but I just realized that I forgot to mention one important thing in the notebook file, which is that you can go into File and you can download, which doesn't really help because those are not formats that are easily worked with unless you are using this software. But you can print. And when you print, you can use print to PDF. You can get a document that you can use and upload, and you can submit the entire notebook file. All right, now with that, I can say I'll wrap up here. Thank you for joining me, and I'll see you next time.